Hello, this is Christian Holter again. So today we'll be talking about how to design novel GLP-1 class drugs to treat CNS diseases. The drugs that are on the market, like Ozempic or Mounjaro, they have been designed to treat diabetes or weight loss. So those drugs stay in the blood for a long time because they have to in order to treat diabetes. So these are once weeklies, which means they stay in the blood for way over a week. But that means that they cannot really cross the blood-brain barrier to get into the brain. So we really need new drugs that can get into the brain to treat diseases such as Parkinson's disease. So I hear you say, what's the blood-brain barrier? And it's actually a protective barrier for the brain. The brain is a very delicate organ and it cannot tolerate big changes. And of course, in the blood, you will have changes all the time. After a meal, the blood sugar levels go up, and then later on they go down again. But neurons cannot tolerate such changes. If you have not enough blood sugar in the brain, then you might just faint. So, therefore, the blood-brain barrier does a very good job in keeping things very tightly controlled. Here's a drawing that tells you that there are all kinds of different transporter systems that can selectively transport important things, certain proteins, hormones, glucose, into the brain. And this way it can keep the concentration in the brain quite stable. So there are actually transporter systems for GLP-1 and GIP, and we have seen before that the older drugs can protect the brain, and mainly it's because their half-life in the blood isn't very long, so they can enter the brain, not very well, but they can. Well, the newer ones are designed to stay in the blood, so they don't really get into the brain very much, only very small amounts. So we developed a novel dual GLP-1 GIP receptor agonist that's designed to actually get into the brain faster. It has been modified. It has an amino acid sequence that's recognized by a transporter and that can then get it into the brain. So this drug doesn't stay in the blood for very long because it's not designed to treat diabetes, but therefore it can move across the blood-brain barrier. So here's a study where people in Seattle tested different types of these drugs. They radio-labeled them and then measured how much of it ends up in the brain 1 hour later. So you can see there's tirzepatide, Mounjaro, semaglutide, Ozempic, liraglutide. They're all designed to stay in the blood, so you can see they don't get into the brain an awful lot. The older drugs like lixisenatide and exenatide, they do get into the brain, at least a bit. And then there's our dual agonist, which is designed to get in, and it does that very well. So the question now is really, does that make a difference? And semaglutide is a very good drug, very effective. Maybe it's good enough. Maybe that's all you need. You don't really need to get it into the brain. So we tested our dual agonist and compared it with the effect of semaglutide in a Parkinson model, and we found that motor impairments were protected and reversed much more by our dual agonist than semaglutide. And when you look at the neurons in the brain that actually produce dopamine and which die in Parkinson, it was clear that the dual agonist can protect neurons much better. Here's an example of such a study. You can actually see the dopaminergic neurons. They're labeled with a fluorescent marker. You can see the images in the center. The upper left square, that's the control. Upper right is Parkinson. Lower left is semaglutide. And lower right is our dual agonist. So you can see the dual agonist protects neurons better because it gets into the brain better. The same goes for the levels of dopamine in the brain, but in Parkinson a lot less dopamine is produced, and the drugs can improve that, but semaglutide isn't that good at it, while our dual agonist increases dopamine levels much better. We also studied tirzepatide, and we could show that it's not very effective. When you look at the dopaminergic neurons, you can see tirzepatide has some effect, a small effect. Exenatide is better, it gets into the brain better, and our dual agonist is even better because it's a dual agonist and it gets into the brain better than exenatide. So we know from clinical trials that drugs that can get into the brain are more effective. Exenatide, the very first drug that was brought to the market to treat diabetes, has a short survival time in the blood, so that means it can get into the brain, and it showed good effect in a clinical trial in Parkinson patients. While another drug called NLY-01 from the company Neurally, which is just exenatide that has been modified. It has a very long molecule attached to it so that it stays in the blood for longer, but it doesn't really get into the brain much and didn't really show much effect in a trial. So here, just a reminder, the phase 2 trial with exenatide showed effect in standard motor tests. The blue line is the drug group, and they showed good scores in the motor tests even 3 months after they stopped giving the drug, while the placebo group, those patients just got worse and worse over time. This Neurally compound, a pegylated version of exenatide, you can see the drawing here. This is actually a very large molecule. It's more than 10 times the size of just exenatide on its own. So it stays in the blood for a long time, but doesn't get into the brain very well. And in a phase 2 clinical trial, it didn't show any effect, didn't improve Parkinson at all. And here just a study to show that this Neurally compound does not actually enter the brain. The gray bars here is the amount of the drug that gets into the brain in wild-type normal mice, and the blue bars show the drug concentration in the brains of transgenic mice that model Parkinson. And these mice have a leaky blood-brain barrier. So yes, in conclusion, we know that GLP-1 class drugs can protect the brain if they're designed to get into the brain. If they can't get to the brain, then the effect is zero. So our dual agonists have been designed to enter the brain very well, and the first preclinical trials showed that it's very effective and better than the drugs that are on the market. And we now have tested the drug, our dual agonist, in the clinic. The trials have started, so stay tuned for further updates. And that's all for today. Thank you for watching, and you can always find more information on my website or actual research papers. If you're a scientist, have a look at my ResearchGate website. You can download reviews or papers on specific research topics for free. And I hope to talk to you very soon.